All right, so this is 6.7 where we're talking about exponential and logarithmic models. So what we're really doing is we're doing um, the real life application where we go back and forth between the two forms. So we're going to ignore this because I'm going to go over it with you. The first thing we're going to do is look at this equation up here. So we're going to say, hey, what does this equation mean? This equation is how we use half-lives and double-lives and multiplications. So the A is the amount that we're talking about. A sub 0 is our initial amount, right? Notice this looks kind of like the PERT equation we did with the continuous. Same idea. That's our initial. That's what we started with. E is the same E we've been talking about. And then K is your rate, like the rate it's increasing or decreasing. If we're talking about a half-life, we're going to use this K. And this T is the years they tell us as part of the half-life. If it's a doubling rate, then we're going to use this one with the K sub 2. And again, this T is the years in the doubling rate. Years in double. Then in this equation, the T is what we're looking for, the time we're looking for. So I know it can get a little confusing with the two T's, but I'll show you what I mean. All right, let's look at this first one. A bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bone? The half-life of carbon-14 is 5,730 years. So I'm never going to make you know the half-life. So since it's half-life, we're going to find our K. So K is going to equal negative ln2 over the years in the half-life. So 5,730. If I type that in the calculator, clear. Okay, so negative ln of 2 divided by 5,730, I get negative 0.00012. So we're going to use that as our K. Now we're going to fill out the equation. So it contains 20% of its original carbon. We don't know what the original is, so we're going to still leave A0. And 20% of that is like saying 0.20 times A0. So of always means times. So it's 20% times the original equals the original. Then we have our E. And then in the exponent, we put the K we just found times T. Now we're going to work backwards to find that T. First thing we're going to do, divide by that A sub 0 to get rid of it since we don't know it. So what we're left with is 0.20 equals E to the negative 0.00012t. To get rid of the E, we're going to take the ln of both sides. So if I take the ln of this side, we get ln of 0.20. And then if I take the ln of this side, it cancels, and we're left with 0.0012t. To get the t alone, we're going to divide. One, two. So I would get ln of 0.20 divided by negative 0.00012 equals t. And then if I type that in the calculator, ln 0.20 divided by negative 0.00012. So we get 13,411.98 years. So that's a really old bone. Now, you may be going, why the heck did she do ln over here? If you remember back to our rules, log base E is the same as ln. And if you take the log, if you have a log of something and the base and the argument are the same, they cancel and you're just left with the exponent. So this would equal k. That all gets canceled. That's why we choose ln, because we want to cancel the e. So taking the ln of e leaves us with just the exponent. And I don't know where that went, but it was ln 0.20 over negative 0.00012. And that gave us 13,411.98 years. And it says to the nearest year, so 13,412 is what we would give for the answer. So that's one way to use this. Now let's do another one. Cesium-137 has a half-life of about 30 years. So half-life 30 years. If we begin with 200 milligrams, how much will remain after 20 years? So again, we're doing half-life. So we want to find K. K is going to be negative ln2 over the half-life, so over 30. If I type that in the calculator, negative ln2 over 30 gives us negative 0.023. So we have that. Now we're going to figure out our equation. So the original amount is 200. So that's our A sub 0. E is E. We just figured out K, so negative 0.023. And they tell us T is 20. So we're trying to figure out the amount of cesium that's left after 20 years. So we can type that in the calculator. So we type 200. And then don't forget to get the E, you're going to hit second, which is the blue button, ln. And then you can type your exponent. So negative 0.023 parentheses 20. So that gives us 126.26 milligrams, because that's what we started talking about. Why is this having a moment? Milligrams. So if they give you the year, you're just plugging stuff in. That's all that matters. Okay, let's do one more. A population of bacteria doubles every hour. So now we're going to use the other K. We're going to use the double time, which is just positive. So let's figure out our K. K equals positive ln2 over every hour, so over 1 hour. If we plug ln2 into the calculator, ln2, we get 0.693. So that's going to be our K. Let's see. Now we start with 10 bacteria. So that's our initial. Then we do E. And our exponent is the K we just found times T. Now pay attention. This is every hour and our time's in hours, so we're good. If they were different, we'd have to change. But we don't, so let me do that. 75. So 10 e to the 0.693 times 75. So we get 3.736. And notice on the end over here, you see E23. That's the same as scientific notation. So it's like saying 3.736 times 10 to the 23rd. That's really big. That's a lot of bacteria. It means there's 23 zeros after this decimal point. Okay. So that's that first part. That's how it is after 75 hours. The next question is find it after 200 minutes. So that's that part where I said we have to pay attention. So 200 minutes, if we divide that by 60 minutes, because there's 60 minutes in an hour, we get 3.33 hours. So this pink is how much bacteria there is after 75 hours. The yellow is going to be the 200 minutes. So we're going to do that same equation, 10 to the E, or 10 times E to the 0.693, but now instead of 75, we're going to do 3.33. So 10 E 0.693 times 3.33 gives us 100.51 bacteria. So in 3 hours, there's only 100. In 75 hours, there's 3 with 23 places after. That's a ton of bacteria. It grows really fast. It's gross. But that's the modeling part. It's using that equation up there. And again, those same things are going to be in the notes. So that is 6-7. Please let me know if you have any questions.